You know, usually when we talk about a medical diagnosis, there's this expectation of just absolute precision. Like you break your arm, the X-ray shows that jagged white line, and the doctor just points at it and says, there it is, broken or not broken. It's binary.
Yeah, it's incredibly comforting, honestly. I mean, humans are just wired to prefer things that are visible, categorized, and, well, definitive.
Right, but then you step into fields where that X-ray machine is just utterly useless.
Yeah.
And we're looking at a world today that is the exact opposite of that clean binary diagnosis. I mean, we are opening up a massive stack of engineering blueprints, regulatory frameworks, testing standards to explore a domain where being murky gets you grounded. Or, worse, causes a catastrophic disaster. So welcome to the deep dive. Today, we are tearing apart exactly how a modern, high-end, unmanned aerial vehicle, a UAV, is designed completely from the ground up.
And we really have to be clear about the stakes right away here.
Yeah.
Because we need to forget the plastic quadcopter you bought at the hobby shop.
Right, the one that gets stuck in a tree.
Exactly. We are focusing on industrial, commercial, and, tactical UAVs. These are machines designed to inspect high-voltage power lines in freezing mountains or deliver critical medical supplies across densely populated cities.
Mm-hmm.
They aren't just remote control planes anymore. The industry actually has a very specific term for them now. Systems of systems, or SOAS.
I really love that phrase, system of systems, because it just captures the absolute chaos of the engineering process. Like, you can't just bolt a bigger battery onto the frame and call it a day.
Oh, absolutely not.
Every single component, the propeller, the battery, the software, the structural carbon fiber, it's all in this constant dynamic negotiation with every other component. And they are all fighting against what seems to be like the ultimate boss-level engineering challenge in aerospace, which is SWaP-C.
SWaP-C, yeah. Size, weight, power, and cost. It's the inescapable gravity of aerospace design.
Right. So imagine for a second that you want a drone that can fly for, say, 10 hours to patrol an oil pipeline. Your first instinct is, okay, well, just add a bigger battery, right?
Which is what a lot of people think, yeah.
But you've just increased the weight. So now your original motors aren't strong enough to lift it, so you have to swap in bigger motors. But bigger motors draw far more power, which means they drain that massive new battery way faster than you calculated.
Right, and oh, by the way, now the drone has ballooned to the size of a refrigerator, and the cost has just skyrocketed past $1 million.
Exactly. It's this vicious, non-linear trap.
It really is. Because if you change a single variable, even just the slight curve of a propeller blade, 50 other variables instantly react. So our overarching mission for this deep dive is to explore exactly how you achieve what they call whole aircraft design optimization and system integration. Basically, how do engineers thread the needle of SWaP-C without the drone just simply falling out of the sky?
And it requires mastering aerodynamics, thermodynamics, material science, artificial intelligence, and which is kind of surprising, international regulatory law, all at the exact same time.
Which is intense.
Yeah. And that's actually where we have to start, because before you even fire up your CAD software to design a cool-looking wing, this machine has to exist on paper within a shockingly rigid legal framework. Like, the days of taping some foam together and flying it over a city are just long gone.
Oh, yeah. The aviation authorities have completely caught up, and their approach is fascinating. If you look at frameworks like the SC-like UAS, that's the European Union Aviation Safety Agency. By the way, they have completely overhauled how they view risk.
All right.
They've built this system specifically for medium to high-risk commercial operations. So if you are flying a heavy drone over a populated area or, operating beyond visual line of sight, you fall into what they designate as SAIL 3 to 6 categories.
SAIL, that's the specific assurance and integrity level, right?
Yes, and if you hit those higher SAIL levels, the drone doesn't just get like a quick safety check by a guy with a clipboard. It is subjected to the exact same design assurance processes as a commercial airliner. You are literally required to get a full type certification.
Okay, I have to stop you right there, because treating a, say, 100-kilogram drone like an Airbus carrying 300 people, that just sounds absurd on its face. The scale of the risk is completely different.
It sounds totally absurd until you realize what EASA is actually doing with their SORA framework.
Yeah.
That's the Specific Operations Risk Assessment.
Right.
Because SORA is brilliant in that it refuses to just ask, how heavy is this machine?
Right.
Instead, it dynamically calculates two distinct metrics. You have your ground risk class, or GRC, and your air risk class, the ARC.
Let me guess. Ground risk is the statistical probability of it just falling out of the sky and crushing a pedestrian, while air risk is the chance it, gets sucked into the engine of a passing Cessna.
Essentially, yes.
Right.
So think about it. A 50-kilogram drone flying over a completely empty desert has a massive ARC if it's operating near an airport, right?
Yeah.
But it has a near-zero GRC because there's nobody underneath it. But you take that exact same drone and hover it over a crowded football stadium, and suddenly it has a terrifying GRC. Sora calculates the interplay of those risks dynamically, and based on that math, you get your sail level.
Yeah.
But here is where it gets truly intense. They don't just certify the physical machine, they certify the entire organization that built it.
Yeah, I saw this in the notes. The alphabet soup of credentials. Like a PDOA or DOA, which is Design Organization Approval, and POA, Production Organization Approval. So if I want to build these commercial drones, it's not enough to bring a perfectly working prototype to the regulators. It's like forcing my entire manufacturing company to pass the bar exam before we are even allowed to design the wheels.
That is a phenomenal way to look at it, actually. Because EASA is effectively saying, we don't care that your prototype works today. We need absolute, documented proof that your engineering culture, your quality control pipelines, and your theoretical understanding of physics are so bulletproof that every single drone you manufacture for the next decade will be safe. They use what's called an objective-based framework.
And I dug into this objective-based concept. It fundamentally shifts the burden of proof. The regulators don't hand you a manual saying, hey, use this specific brand of titanium bolt. They say, here is an objective. Prove to us that if this primary flight controller touches fire at 5,000 feet, the aircraft will not crash.
Precisely. They demand a 100% success rate on fail operational triggers.
100%.
Yes, the entire system must fail safely.
Right.
You have to mathematically prove how the drone recognizes the failure, isolates the short circuit, hands over command to a redundant backup, and autonomously executes a safe landing.
And they put a hard number on this reliability, too. For these high-tier operations, the requirement is often a mean time between failures MTBF of greater than or equal to 150 hours. Now, if you are listening to this and thinking about your daily commute, 150 hours sounds kind of pathetic, right? Your Honda Civic runs for thousands of hours without the engine exploding.
Well, sure, but you aren't operating your car in an inherently unstable three-dimensional environment while constantly fighting gravity. In the context of an experimental, highly complex, high-vibration flying machine that's packed with lithium batteries and spinning carbon fiber, 150 hours of guaranteed, mathematically proven failure-free operation is a monumental engineering task.
Because it's not just 150 hours of gentle hovering in a quiet gymnasium. EASA maps that MTBF against a very specific mission profile. Extreme thermal loads, sudden wind shear, maximum payload stress. You actually have to prove that your system's failure rate follows an exponential distribution model.
Right, the classic reliability equation. It's R of t equals e to the negative lambda t, where RT is the reliability over time, E is Euler's number, and lambda is the constant failure rate. You literally have to push that lambda value so incredibly low that the probability of a critical system loss during that 150-hour window is virtually indistinguishable from zero.
Okay, so you've passed the organizational bar exam. You have your type certification pathway clear. Now you have to actually build the physical bones of this machine, and you have to do it without violating those swap-C constraints we talked about. If the legal framework demands perfection, how do you build a drone that is incredibly light but won't snap in half the first time it hits a thunderstorm?
You start by deliberately trying to destroy it in a laboratory.
Naturally.
The guiding standard here is ASTM F2416. It dictates the structural design and the one-to-one physical static and load testing. And note, there are no scale models allowed here.
No tiny wind tunnel models.
Nope. You take the actual full-size carbon fiber wing, you bolt it into a massive steel jig, and you use hydraulic rams to pull on it until the composite materials start to scream.
I was looking at the numbers for these tests, and they're wild. Critical joints, like the wing root where the main wing attaches to the fuselage, have to withstand a 2.5 G operational limit load. So if this drone weighs 100 kilograms fully loaded, that single joint has to comfortably hold 250 kilograms of shear bending force.
And comfortably is the key word there. That 2.5 G is just the operational limit. That's what it might experience pulling out of a steep dive. But ASTM F2416 also demands an ultimate load verification. And this is 1.5 times the maximum expected stress.
So you take that 2.5 G load, you multiply it by 1.5, giving you 3.75 G. Under that ultimate load, the standard explicitly states the structure is not allowed to catastrophically yield or break. Now, yield is a very specific material science term. I'm assuming that doesn't just mean snapping in half.
Right, yielding is the threshold where a material stops behaving elastically and starts behaving plastically.
Okay, explain that.
Think of a paperclip. If you bend a paperclip a tiny bit and let go, it snaps perfectly back to its original shape, right?
Sure.
That's elastic deformation. But if you bend it past a certain point, it just stays bent. You've permanently deformed the internal crystalline structure.
Yeah.
That is plastic deformation or yielding.
So the regulators are saying even if the drone gets hit by an unprecedented microburst of wind that subjects it to 1.5 times the maximum theoretical force it was ever designed for, the wing might stay permanently bent, the drone might be totally written off by the insurance company the moment it lands, but it will absolutely not snap off and fall on a school.
Exactly. It fails safely. That's the objective.
But hearing this, my immediate uneducated instinct is, if we need it to be that indestructible, why not stop messing around with thin carbon fiber and just build the critical joints out of solid blocks of aerospace titanium? Like, overbuild it.
Which throws you headfirst back into the swap-C meat grinder. Wait. If you use solid titanium, the structural team is thrilled. They give each other high fives because it passes the ASTM test effortlessly. But the aerodynamics team suddenly realizes the drone is way too heavy to generate lift, so they demand a bigger wing. The bigger wing adds more weight and drag, so the propulsion team demands a massive battery. The battery takes up the entire payload bay, meaning there's absolutely no room for the expensive camera the customer actually wants.
It's the classic siloed engineering problem.
Yeah.
Linear design. Team A finishes their part, tosses it over the wall to Team B, who immediately has to compromise it.
And that's why linear design is completely dead in modern UAV development. The solution is MBO, multi-disciplinary design optimization. This is a massive paradigm shift. Utilizing computational frameworks like OpenMBAO and MFEs, engineers throw out the silos. They force powerful computers to simultaneously calculate the aerodynamics, the structural mechanics, the thermal heat of the motors, and the battery drain all at the exact same millisecond.
They are essentially tossing all the laws of physics into a giant digital blender.
Pretty much.
And by doing this, they find these incredibly counterintuitive, hidden efficiencies, especially when it comes to the air the drone is flying through, because a UAV operates in a very weird, frustrating fluid dynamic space that is governed by the Reynolds number.
Oh, the Reynolds number is crucial here. In fluid dynamics, it's a dimensionless number that basically describes the ratio of inertial forces to viscous forces.
Let me see if I can translate that for a second. So viscous forces describe how sticky or thick a fluid feels, like honey versus water. And inertial forces describe the raw momentum of the object smashing through that fluid.
Right.
So if you're a giant Boeing 747 blasting along at 600 miles an hour, your inertial forces are astronomical. To a 747, the air feels thin, crisp, and easily separated. That's a high Reynolds number.
Conversely, if you are a microscopic fruit fly, your mass and speed are so incredibly low that the inertial forces are tiny. To a fruit fly, the air feels viscous, almost like swimming through thick syrup. That's a low Reynolds number.
So where does our 100-kilogram drone sit on that scale?
Right, in the worst possible middle ground. UAVs typically operate at a Reynolds number between 10 to the 4th and 10 to the 5th. At this specific scale, the air isn't crisp like a 747 experiences, but it's not thick syrup either. It's just sticky enough to cause massive aerodynamic headaches. And the most notorious of these is the laminar separation bubble.
Laminar separation bubble. It sounds pretty harmless, but I'm guessing it's the absolute enemy of swap-C.
It destroys efficiency. So imagine the air flowing beautifully and smoothly over the curved front edge of a propeller blade. That's laminar flow. But because of the specific sticky Reynolds number, the airflow suddenly detaches from the surface of the blade. It creates a tiny localized pocket of swirling, violent turbulence, that's the bubble, before reattaching further back down the blade.
And that bubble acts like a parachute, creating massive aerodynamic drag and just killing your lift. What's wild is that because of these bubbles, the classical math we've used for decades to design propellers, stuff like blade element momentum or BEM theory, which works perfectly for massive wind turbines and helicopters, completely breaks down here. It just can't predict where these bubbles will form on a tiny drone propeller.
Exactly. So historically, engineers had to fall back on CFD, computational fluid dynamics. You build a 3D model of the propeller, put it in a virtual wind tunnel, and let a supercomputer crunch the Navier-Stokes equations to simulate every single molecule of air. But CFD is notoriously agonizingly slow. Simulating just one slight twist of a propeller blade can take a supercomputer days.
And you obviously can't run an MDO framework if you have to wait 3 days every time you tweak the wingspan by a millimeter. So they bring in artificial intelligence. They completely bypass the supercomputer entirely using a hybrid AI proxy model, specifically a CNN LSTM architecture.
This is where software engineering really meets fluid dynamics. So a CNN is a convolutional neural network. It's actually the same technology your phone uses to recognize faces in photos. It's brilliant at understanding complex spatial patterns. And the LSTM is a long, short-term memory network, which is designed to understand sequences and dependencies over time.
Why do they need both of them, though?
Because the airflow over a blade is both spatial and temporal. The physical shape of the blade creates a spatial pressure field, but that airflow evolves over time as the propeller spins. So they feed thousands of slow, expensive CFD simulations into this AI. The CNN LSTM learns to recognize the fundamental patterns of fluid dynamics. Once it's fully trained, the AI can predict the aerodynamic performance of a brand new propeller shape in milliseconds, with almost the exact same accuracy as the supercomputer.
Okay, so you have this lightning-fast AI aerodynamicist. You plug it into an optimization algorithm called NSGA2. And this algorithm's only job is to wildly mutate the shape of the propeller, tweaking the twist, stretching the chord length, bowing the wingspan literally millions of times a second. It's like this evolutionary race to find the absolute perfect geometric shape for that specific sticky Reynolds number.
And it finds solutions human engineers would never manually try. For instance, the AI heavily utilizes gurney flaps.
What are those?
They are these microscopic vertical lips added to the very trailing edge of the propeller blades. To a human, they look like manufacturing defects, but they perfectly manipulate the pressure differences at the back of the blade. Using this AI-driven approach, they can hit an aerodynamic efficiency of 82.0% in cruise conditions, which is phenomenal.
But we can't forget the MDO, right? Multi-disciplinary. The AI is twisting the blade to get that sweet 82% efficiency, but simultaneously, the structural algorithm is constantly yelling, "Stop! You just made the blade too thin. It's going to snap and fail the ASTM 2.5G test."
Exactly. The structural side is continuously running von Mises' stress calculations.
Von Mises stress being the mathematical formula that predicts exactly when a complex 3D object will hit that plastic yielding point we talked about earlier.
Right. So the MDO forces a ruthless compromise. The AI wants a paper-thin, aerodynamically perfect blade. The structural math demands a thick, heavy, indestructible club. They fight it out mathematically for millions of iterations until they find the exact geometry that satisfies both. And the result? By jointly optimizing this high-fidelity geometry, engineers can reduce the propeller shaft power required to keep the drone in the air by a staggering 11.8%.
11.8% less power needed to fly, purely through AI-sculpted geometry. That is a colossal victory for SWaP-C, because that means you can use an 11% smaller battery, or carry 11% more cargo, or fly 11% further without adding a single gram of weight.
It fundamentally changes the capability of the aircraft. But as beautiful as an AI-optimized skeleton is, it's just a glider. It needs a beating heart. It needs something to generate the immense thrust and electrical power required for a 24-hour mission.
Which brings us to the engine units and the FADEC system. Now, I have to be honest, when I first looked at this section of the research, I felt like I had stepped back in time. We hear so much about the electric revolution. Cars are going electric, small drones are entirely electric. I naturally assumed these massive commercial UAVs were just running on giant lithium battery packs. But they aren't. They rely heavily on internal combustion engines, ICEs, burning gasoline or heavy aviation fuel. Why on earth are we still burning fossil fuels in cutting-edge drones?
It all comes back to a single, brutal metric.
Yeah.
Energy density. Lithium-ion batteries have completely revolutionized our world, but mathematically, they cannot touch the raw, concentrated chemical energy packed into a single kilogram of liquid fuel.
Right.
If you are designing a UAV that needs to loiter over a forest fire for 20 hours straight, pure electric propulsion is just physically impossible right now.
Yep.
The battery pack required would be so massive, the drone wouldn't even be able to lift its own weight off the runway.
Okay, so they use a gas engine. But they aren't just strapping a modified lawnmower engine to the fuselage and hooking it directly to the propellers. They use a hybrid propulsion architecture. They couple these internal combustion engines directly to BLDC or PMSM generators.
Brushless DC or permanent magnet synchronous motor generators. The gas engine's primary job isn't always to spin the propeller directly. Often its job is just to spin that generator at high RPMs, That produces a massive continuous flow of highly efficient electrical power, which then drives the actual flight motors.
But anyone who has ever tried to start a gas-powered snowblower in the freezing cold knows that small internal combustion engines are really finicky. Operating one dynamically at 15,000 feet where the air is freezing and thin sounds like a reliability nightmare. Traditional aircraft engines rely on carburetors to mechanically mix the liquid fuel with the incoming air.
And carburetors are entirely obsolete in this tier of UAV design. They are mechanical, they are incredibly slow to react to atmospheric pressure changes, and most dangerously, the Venturi effect inside a carburetor causes a massive temperature drop.
So they freeze.
Exactly. At high altitudes, the moisture in the air instantly freezes inside the carburetor, choking off the engine. And a stalled engine over a populated area triggers a catastrophic sales 6 scenario.
So you completely strip out the mechanical carburetor, you modernize the internal combustion engine by handing absolute control of the combustion cycle over to a computer. Enter FADEC, full authority digital engine control.
Full authority means exactly what it sounds like. There is no mechanical override. The computer has absolute power over the life and death of that engine. FADT utilizes a highly complex closed-loop control system fed by a dense network of sensors. It constantly reads MEP manifold, absolute pressure, IAT intake air temperature, CHT cylinder head temperature, and EGT exhaust gas temperature.
Imagine having an autonomous, microscopic DJ living inside the engine block. But instead of perfectly mixing a transition between two songs, this DJ is perfectly mixing liquid fuel and oxygen. It looks at the altimeter and notices, okay, we just ascended 5,000 feet, the air's getting thinner, we're running too rich. Instantly cut the fuel injection pulse by 4%. Milliseconds later, it checks the thermal sensors. The cylinder head is getting a bit too hot. Enrich the mixture slightly so the evaporating fuel pulls heat out of metal. It is doing this delicate dance thousands of times a minute.
And that DJ also has total control over the throttle valve itself. In a standard aircraft or older drone, you have a physical braided steel cable running from a servo motor all the way to the engine's throttle body. But mechanical cables introduce hysteresis.
Hysteresis, the absolute enemy of precision. If I pull a metal cable, it stretches slightly. There's friction where it rubs against its housing. So when the flight controller commands open throttle 10%, the actual valve might only open 8% because of that mechanical sop.
And over hundreds of hours of intense engine vibration, that cable slowly frays and stretches even further. So FAD institutes throttle by wire. The physical cable is deleted. The flight computer sends a digital signal via copper wire directly to a high-precision, high-torque servo motor bolted straight to the throttle valve stem. It snaps open instantly with zero mechanical lag.
But remember the regulatory paranoia from earlier. What if that servo motor fails? What if the digital signal glitches and tells the throttle to just slam to 100%? ESA demands fail operational safety.
Which is exactly why FADEC incorporates dual redundant potentiometers on that throttle valve. There are two independent sensors reading the physical angle of the valve. If sensor A reports the valve is 50% open, but sensor B reports it's 42% open, the FADEC computer instantly knows there's a hardware discrepancy. It flags a fault, defaults to a pre-programmed safe operating state, and alerts the flight controller to return home.
The digital precision is incredible, but as I was reading through the engineering standards, there was a detail about the physical maintenance of these engines that completely blew my mind. It proves that in a system of systems, even basic chemistry can bring down an aircraft. I'm talking about the ASTM E70 standard for liquid coolant.
Ah, yes, the coolant pH level. This is a masterclass in how granular aerospace engineering must be.
The standard strictly dictates that for any liquid-cooled engine on these drones, the pH level of the coolant fluid must be constantly monitored and maintained strictly between 7 and 11, basically neutral to slightly alkaline. You can't just run down to the auto parts store and pour cheap green antifreeze into $1 million UAV. Why is the regulatory body writing standards about coolant chemistry?
Because of the material science of swap-C. To save weight, the engine blocks and internal heat sinks are almost exclusively cast from aerospace-grade aluminum. Now, aluminum is wonderfully light, but it is highly reactive. Thankfully, aluminum naturally forms a microscopic oxide layer on its surface when exposed to air or water. This is called a passivation layer, and it acts like a microscopic suit of armor protecting the underlying metal from corrosion.
But as the engine runs for hundreds of hours, thermal breakdown occurs. If the mechanic gets lazy and neglects to check the chemistry and the coolant degrades, becoming even slightly acidic, dropping below a pH of 7.
That slight acidity chemically attacks and strips away the passivation layer. Once that armor is gone, the acidic coolant acts as an electrolyte. Because the engine is made of slightly dissimilar metal alloys, a tiny electrical current begins to flow through the coolant between the metals. This is galvanic corrosion.
Wow.
It literally acts like a battery, electrochemically dissolving the aluminum from the inside out, creating deep microscopic pits.
So, because a mechanic didn't test the pH of the fluid, the engine block slowly dissolves over a month of flying. Eventually, the pitting breaches a critical seal, causing a massive, instantaneous coolant leak at 10,000 feet. The cylinder head overheats and warps within seconds, the engine seizes, and a massive drone plummets into a forest, all because of a slight change in pH.
Exactly. In a system of systems, a failure in fluid chemistry is a failure of the entire aircraft.
It's terrifying and beautiful. So we have a legal framework, we have an AI-sculpted MDO-optimized skeleton, and we have a FADEC-controlled chemically pristine gas engine generating massive mechanical power, spinning a generator to produce high-voltage electricity. Now we move down the chain. How does the drone's brain actually translate that raw electrical power to the motors with enough precision to keep it from tumbling out of the sky?
This is the nervous system, the ESC, the electronic speed controller. And this is where electrical engineering truly crosses into pure mathematics. The flight controller decides, hey, a wind gust just hit the left wing. I need the front left propeller to spin exactly 54 RPMs faster immediately to stabilize. It sends that command to the ESC. But an electric motor is not a simple light switch.
Right. These are large, three-phase, brushless motors. They consist of a stationary ring of copper wire coils the stator and a spinning inner ring studded with powerful rare earth magnets the rotor. To make it spin, you can't just apply continuous power. You have to push pulses of electricity into the copper coils in a highly precise sequence, creating a rotating magnetic field that basically drags the permanent magnets along with it.
In the early days, ESCs used a really crude method called block commutation. They just slammed raw, square-wave pulses of DC power into the coils in a harsh six-step sequence. It worked, but it was noisy, incredibly electrically inefficient, and it created something called torque ripple.
Torque ripple. Basically, instead of a smooth rotation, the motor was micro-stuttering thousands of times a second as it jumped from one magnetic coil to the next.
And that micro-stuttering sends high-frequency vibrations through the entire carbon fiber airframe, which blurs the optical cameras and prematurely destroys the motor bearings. So the modern standard detailed for these UAVs is FOC, field-oriented control. And this is where the microprocessors have to perform real-time mathematical acrobatics.
FOC abandons the harsh square waves. It wants to feed the motor beautiful, perfectly smooth sine waves of alternating current. But calculating the exact timing and voltage for three separate, constantly changing alternating currents, interacting with a rapidly spinning physical magnet is an incredibly complex three-dimensional physics problem.
It's way too complex for a lightweight ESC microprocessor to calculate fast enough. So FOC uses two brilliant mathematical shortcuts, the Clark transform and the Park transform.
Okay, I really want to try to visualize this because staring at the math formulas made my head spin. Imagine you were standing over a record player, and there's a record spinning at 78 RPM. The label in the center is a complex 3D shape, and because it's spinning so fast, you can't read a single word on it. It's just a blur.
Okay.
The Clark transform is a mathematical operation that essentially takes that complex 3D shape and squashes it completely flat onto a 2D plane. It simplifies the geometry. But it's still spinning at 78 RPM. It's still a blur. Then you apply the Park transform. The Park transform is the equivalent of you leaning over the record player and spinning your own head, your own frame of reference, at exactly 78 RPM in perfect sync with the record.
That is a phenomenal analogy. By locking its mathematical frame of reference to the exact rotational speed of the motor's magnetic field, the Park transform makes the spinning chaos suddenly appear completely stationary to the computer.
The blur stops. You can read the label perfectly.
Yes. It decouples the complex, chaotic alternating current into two simple, stationary DC-like values. You have the D-axis, which represents the magnetic flux, the raw magnetic grip the coils have on the rotor, and the Q-axis, which represents the active torque, the actual twisting force being applied.
So by doing these Clark and Park trigonometry calculations thousands of times every single second, the computer can independently control the magnetic grip and the twisting force. It feeds the motor absolute mathematical perfection. The torque ripple vanishes entirely. The motor spins with silent, glassy smoothness, and the electrical efficiency skyrockets.
And because these high-end UAVs cannot afford an ESC failure, the hardware design mandates a 20% to 30% thermal and electrical safety margin. The ESCs are massively overbuilt with heavy silicon carbide MOSFETs, so that even if the drone has to execute extreme emergency maneuvers at maximum throttle for 10 minutes straight, the ESCs will never overheat and desolder themselves.
But the ESCs are just the muscles. They only do what they are told. How do the commands actually get from the main flight controller to the ESCs? What language are they speaking across this nervous system?
They communicate over a CAN bus architecture, utilizing highly robust aviation protocols like Drone CAN or CIFL.
CAN bus controller area network. It's the same fundamental technology used in modern cars. But why use it in a drone instead of just standard USB or Ethernet wiring?
Because a hybrid drone is a spectacularly noisy environment electrically. You have a gas engine firing spark plugs, high-voltage generator spinning, and massive magnetic fields from the motors. This creates intense electromagnetic interference, or EMI. Standard data wires would act like antennas, soaking up that interference and corrupting the signals. The CAN bus uses differential signaling. It sends the same data signal down two twisted wires simultaneously, but essentially inverted. When the ESC receives the signal, it compares the two wires. If a spike of electromagnetic noise hits the wire, it hits both equally. The computer mathematically subtracts the noise and reads the pristine original signal.
It's brilliantly resilient, and they push data across this bus at 1 megabit per second. But the protocol rules dictating when data can be sent are fascinating. The flight controller is constantly managing data traffic. General telemetry, like the ESC reporting its internal temperature back to the ground station, is given low priority. It updates at a relaxed 10 to 50 hertz. But the core throttle commands.
The core throttle commands the flight controller, demanding a motor speed up or slow down, or strictly limited to a maximum processing latency of 2 milliseconds.
0.002 of a second. Why is that absolute speed so critical?
Think about the physics of hovering. A UAV hovering in turbulent air is an inherently unstable dynamical system. Imagine trying to balance a heavy broomstick upright on the palm of your hand during a windstorm.
Very difficult.
If a gust of wind hits the drone, the MEMS gyroscopes detect the tilt instantly. But if the communication bus is clogged, and it takes 15 or 20 milliseconds to tell the motors to counteract the tilt, it's too late. Gravity has already pulled the airframe past its point of aerodynamic recovery. The drone will flip. The 2-millisecond latency limit ensures the thrust vectoring happens faster than gravity, and wind can destabilize the mass.
Incredible. Okay, we have the bones, the heart, and the nervous system. Now we arrive at the brain, specifically the brains of energy, segments 5 and 6 of our outline, the BMS and the smart EMS. Because we have an incredibly complex power ecosystem here, we have a gas engine generating power. We might have thin film solar panels embedded in the carbon fiber wings trickling in power. And we have a high voltage lithium battery pack acting as the primary buffer. How on earth does the drone decide which power source to draw from at any given millisecond without draining the battery or stalling the engine?
It is handled by a layered hierarchy of intelligence. The foundation of that hierarchy is the BMS, the battery management system. Its entire existence is dedicated to the safety, longevity, and monitoring of the lithium cells. It continuously performs active cell balancing.
Because a high-voltage battery isn't just one big block, it's hundreds of individual lithium cells wired together. If one cell gets slightly more charged than the others, it can overheat. The BMS constantly shuffles energy between the cells so they all degrade at the exact same safe rate.
Exactly. It rigorously calculates the precise SOC state of charge, meaning exactly how much usable energy is left down to the milliamp, and the SOH state of health, analyzing the internal chemical resistance to determine how degraded the battery is over its multi-year lifespan.
And the physical safety requirements for these battery packs are absolutely brutal. Under standards like UL 2272 and UL 3030, they don't just review the BMS software, they inflict physical trauma on the hardware. They take a fully charged, fully energized, high-voltage battery pack and drop it from 1.5 meters, about 5 feet, directly onto solid concrete.
And it is not a single drop test. They repeat the impact 6 times, intentionally striking all 6 different geometric faces of the battery casing to test every possible structural weakness.
And after being repeatedly smashed into concrete, the standard dictates there can be absolutely no fire, no thermal runaway, and no venting of highly toxic, flammable electrolyte gas. The moment the battery impacts the ground, the BMS accelerometers must instantly detect the physical shock, trigger explosive physical disconnects to isolate the high-voltage contactors, and render the entire pack chemically and electrically inert before a short circuit can spark a fire.
The BMS handles the raw survival. But above the BMS sits the brain, the smart EMS, the energy management system. This is where we cross into advanced artificial intelligence and dynamic control theory. The EMS uses a hierarchical ladder of algorithms to allocate power. Let's start at the bottom of the ladder. Adaptive control.
Right, because even a perfectly engineered drone ages. After 2,000 hours of continuous flight operations, the piston rings in the gas engine wear down and lose compression. The internal resistance of the lithium battery permanently increases. The hardware drifts from its original factory specifications.
If the flight controller doesn't realize the hardware has aged, it will send commands that the hardware can no longer physically execute, leading to instability.
Yeah.
So the EMS utilizes MRAC model reference adaptive control combined with RLS recursive least squares algorithms.
Okay, let's break that down. What is the drone actually doing with MRAC and RLS?
The drone maintains a perfect mathematical model reference in its memory of exactly how the engine should respond. It constantly compares this perfect model against reality. If it commands 50% throttle and the engine responds a few milliseconds slower, or produces slightly less torque than it did when it was brand new, the recursive least squares algorithm instantly flags that discrepancy. It recognizes the engine is wearing out.
So what does it do? Does it just flag a maintenance warning?
It's much smarter than that. It dynamically rewrites its own fundamental control math. It adjusts the PID control gains the proportional, integral, and derivative values that dictate how aggressively it pushes the engine in real time to perfectly compensate for the mechanical wear and tear.
That is mind-bending. It is a self-tuning machine. It literally heals its own software to accommodate its degrading hardware.
Exactly. Moving one step up the hierarchy, we encounter fuzzy logic control, or FLC. Traditional computer logic is incredibly rigid. Boolean logic is black and white. If temperature is exactly 100 degrees, turn on fan. But the atmospheric environment is a chaotic gray area. So the EMS takes the precise numerical data from its sensors and translates it into fuzzy language using what are called membership functions.
So instead of dealing in hard numbers, it categorizes the data into human-like concepts. It turns numbers into states like the error is quite large, the error is tiny, or the temperature is dropping rapidly.
And here's the genius of it. The boundaries of those fuzzy membership functions are not static. They are dynamically adapted by the atmosphere via reinforcement learning.
Give me an example of how that works in flight.
Imagine the drone is flying at sea level in thick, dense air. A 5-degree deviation from its flight path might be considered a large error because the air is thick and easy to grip, so it aggressively corrects it. But then the drone climbs to 15,000 feet to cross a mountain range. The air pressure drops drastically. The air is thin.
If it tries to aggressively correct a 5-degree error in thin air, it might overcompensate and flip over.
Precisely. So the reinforcement learning model detects the drop in air pressure and automatically stretches the fuzzy logic boundaries. What was considered a large error at sea level is now mathematically redefined as a tiny error. The drone relaxes its control inputs. The core logic of the aircraft literally bends and adapts to fit the atmospheric pressure around it.
Okay, that is brilliant. But that brings us to the absolute top of the EMS hierarchy, the grandmaster orchestrator of the entire energy system. Model Predictive Control, or MPC. When I was digging through the engineering papers for this deep dive, they actually published the core mathematical cost function used by the MPC algorithm. It is heavily utilized for energy allocation, and they often combine it with Hamiltonian functions or simulated annealing to find global optimums. But I need you to break down this base equation, because it looks like ancient Greek to me. The equation is J of x, u equals the sum from k equals 1 to n of the norm of x sub k minus x ref squared weighted by q, plus the norm of u sub k squared weighted by r, plus lambda times delta SOC sub k.
You are looking at the absolute pinnacle of modern dynamic control theory. That equation is not just reacting to the present, it is literally forcing the drone to predict the future and calculate the mathematically perfect way to exist within it. It utilizes what we call a receding horizon optimization.
A receding horizon. Let's use a driving analogy here. If you are a terrible driver, you just stare at the bumper of the car 10 feet in front of you, you are constantly slamming on the brakes and mashing the gas, reacting purely to the immediate present. It's incredibly inefficient. But if you are an expert driver, you're looking 200 yards down the highway, you anticipate a curve coming up, you see brake lights far in the distance, and you subtly adjust your gas pedal and steering inputs to smoothly navigate the next 10 seconds of time. As you drive forward, that 10-second window of prediction moves forward with you. That is your receding horizon.
That is a perfect translation. The MPC is the expert driver. It is constantly projecting a mathematical horizon several seconds into the future. And it uses that J of x view equation to score how well it plans to drive. Let's break it down piece by piece. What is the first chunk, the x sub k minus x ref part?
Okay, x sub k represents the drone's predicted actual state at a future moment where it thinks it will be, its speed, its altitude. XREF is the reference state where the pre-programmed flight path says it should be. So X sub k minus XREF is simply the error. It's how far off course the drone predicts it will drift. The drone obviously wants to minimize this error. And the Q is just a mathematical weighting factor that heavily penalizes large errors.
Spot on. It wants to stay perfectly on target. Now, what about the middle section, the U sub k part?
U sub k represents the physical effort, the control inputs. Pushing the throttle to 100% requires massive effort and burns through your fuel reserves. The drone wants to minimize the physical effort of the motors to maximize its flight time. The R is another tuning weight that balances how much we care about saving energy versus staying perfectly glued to the flight path.
Excellent. And the final, critical piece, lambda times delta SOC.
Delta SOC is the change in the battery's state of charge. It represents draining the lithium battery, and that lambda symbol is a massive penalty multiplier. The algorithm aggressively penalizes draining the battery, because in a hybrid system, the battery is your emergency lifeline if the gas engine fails.
So, synthesize all of that.
Yeah.
What is the MPC actually doing hundreds of times a second?
It is running massive simulations of the immediate future. It calculates, I predict a wind gust will hit me in 1.5 seconds. Should I slowly rev up the gas engine to counter it? That takes time and burns fuel, but it saves the battery. Or should I instantly dump 50 amps of pure electric power from the battery to the motors? That will keep me perfectly on my flight path with zero error, but I will trigger the massive lambda penalty for draining my emergency reserve. It calculates the absolute most efficient, safe compromise between staying on the path, minimizing mechanical effort, and hoarding battery power. And it solves this incredibly complex calculus problem continuously, endlessly while flying.
It is a breathtaking piece of engineering, but it all hinges on one fragile reality. Which brings us to our final segment, segment 7, the code that binds it all. Because here is the terrifying truth about a system of systems. All of this miraculous hardware, the MDO sculpted wings, the flawless FADEC, the real-time trigonometry in the ESC, and the predictive calculus of the MPC is entirely 100% useless if a single line of software code contains a memory leak.
Software crashes are just a fact of life for most of us. Your laptop freezes, your smartphone randomly reboots, and app force closes. We accept it. But if the flight controller software on a 200-kilogram UAV flying over a densely populated city encounters an unhandled exception and reboots, it's not an inconvenience, it is a lethal event. That is why the aviation industry does not write code like Silicon Valley. They rely on RTCA, DO178C for software design, and DO254 for physical hardware logic. These are the undisputed gold standards for aviation software.
And specifically, for these SAIL-3-C drones, we are talking about achieving DLA, Design Assurance Level A.
DALA is the highest possible tier. It is reserved exclusively for software where a failure condition is officially defined as catastrophic, meaning the total loss of the aircraft and the probable loss of human life. The testing and verification requirements to achieve DLA are almost unimaginably strict and astronomically expensive.
Let's look at one specific requirement that highlights this paranoia. MCDC, Modified Condition Decision Coverage. To pass DALA, the codebase requires 100% MCDC.
Let's translate that for anyone who isn't a software engineer. Let's say a programmer writes a single line of code with a complex Boolean logic statement to control the landing sequence. If the altitude is below 500 feet, Andy, the landing gear is fully deployed, or the downward laser altimeter detects an obstacle, then aggressively floor the drone. MCDC dictates that the software tester must mathematically prove that every single one of those individual variables, the altitude, the gear, the laser, independently affects the final outcome. You have to write exhaustive automated test cases for every possible combination of true and false for those variables and prove that the software handles it perfectly without crashing.
And beyond that, the standard states there can be absolutely zero dead code in the final compiled software.
Dead code. Code that exists in the system memory, but theoretically based on the logic pathways, should never, ever be executed during normal flight operations. Maybe it's a leftover diagnostic function from when the engineers were testing it on a desk, or a deprecated feature for a sensor they decided not to use. Why is dead code considered a ticking time bomb? If it never runs, who cares?
Because in aerospace, you have to plan for the impossible. At high altitudes, a drone is subjected to increased cosmic radiation. A stray high-energy particle can strike the physical silicon of the microprocessor and cause a bit flip, literally changing a 0 to a 1 in the computer's memory. Or a bizarre 1 in a billion sequence of sensor glitches can occur. If this happens, the program execution can suddenly jump out of its normal loop and land inside that dead code. Because the code is dead, the testing team never rigorously verified it. It might contain an infinite loop. It might contain a command to wipe the RAM. If the processor enters that untested loop, it freezes. The drone falls out of the sky. DO-178C demands absolute traceability. Every single line of code must trace back to a specific, rigorously tested system requirement. If it doesn't trace, it is ruthlessly deleted.
The level of institutional paranoia is staggering. There are 71 specific objectives that must be documented and met for DALA certification, and 30 of them require independent review.
Independent review is the cornerstone of aviation safety.
But I have to push back here on the sheer economics of this. Is it truly necessary to have an independent reviewer manually check every single Boolean logic path and trace every line of code? Doesn't that make writing the software take 10 times longer and cost millions of dollars more than traditional software development?
It does. It is cripplingly expensive and slow. But we always come back to the fundamental rule of the sky. Undefined behavior results in a crater. The developer who wrote the original code has inherent blind spots. They know how the code is supposed to work. They test the happy paths. An independent reviewer is hired with a completely different mindset. Their only job is to figure out how to break it. They assume the developer is an idiot who made a catastrophic mistake. In aerospace, trust is a liability. You verify everything.
And to further protect this pristine, perfect software from the chaos of the outside world and faulty sensors, they don't run it on Windows or Linux. They run it on an RTOS, a real-time operating system. Architecturals like NetX or ARON-C 653 compliant MRTOS.
An RTOS is fundamentally different from the operating system on your laptop. Your laptop is designed for maximum throughput and fairness. If you are typing a document and an antivirus scan starts in the background, your typing might lag for a second. The OS pauses one task to service another. An RTOS does not care about fairness. It guarantees hard, real-time execution. If the flight controller demands that the ESC motor control loop must be executed every 2 milliseconds to prevent the drone from flipping, the RTOS guarantees with absolute mathematical certainty that it will run every 2 milliseconds, even if the camera system catches fire and starts screaming for CPU resources.
And it protects the core systems using strict spatial and temporal partitioning. I like to imagine the RTOS memory architecture as a heavily fortified apartment building. Spatial partitioning means the core flight controller lives in penthouse A, and the less critical radio telemetry module lives down in apartment B. There are impenetrable, hardware-enforced steel walls between them. If the radio module gets hit by a cyber attack or encounters a memory leak and tries to consume all the RAM, it physically cannot break through the wall to corrupt the flight controller's memory.
And temporal partitioning takes that analogy a step further. It's not just thick walls. It's the landlord strictly controlling time. The landlord dictates that penthouse A gets to use the hallway for exactly 5 milliseconds, and then apartment B gets to use it for 2 milliseconds. Even if apartment B is having a massive emergency and screaming to use the hallway, the landlord absolutely refuses. It forcefully suspends apartment B and gives the hallway back to penthouse A on schedule. The failure is completely contained in time and space.
It is a bulletproof digital fortress. But you can build the most perfect fortress on a chalkboard, and it might still collapse in an earthquake. Before this drone is ever legally allowed to spin its propellers on a real runway, how do the engineers actually prove that all this MDO optimization, FADE control, and DO-178C software works in the chaotic real world?
They put the brain into the matrix. They utilize exhaustive HAL testing hardware in the loop.
Hardware in the loop. So they take the actual physical flight control computer, the exact piece of silicon that will eventually be bolted into the drone, and they plug it into a massive simulation computer, like a SpeedGoat real-time target machine.
Exactly. The flight controller is sitting on a desk in a sterile laboratory, but it doesn't know that. The SpeedGoat supercomputer feeds it beautifully faked, high-fidelity electrical sensor data. It tells the flight controller, "You're currently at 10,000 feet flying 100 kilometers an hour. The air density is this exact value, and you just got hit by a 30-knot crosswind." The flight controller reacts as if it's real. It runs its MPC predictive calculus, it executes its Clark and Park transforms, and it sends electrical signals down the CAN bus, commanding the ESCs to adjust the motors to stabilize the aircraft.
But there are no motors on the desks. The SpeedGoat computer intercepts those CAN bus signals, instantly calculates exactly how the virtual mass of the drone would physically react to that motor thrust, calculates the new aerodynamic vectors, and feeds the updated fake sensor data back into the flight controller. It creates a perfect closed-loop illusion. They even wire the optical camera sensors into video game engines, like Unreal Engine, to simulate the visual environment of flying over a forest.
But the goal isn't just to let the drone fly a peaceful virtual lap. The regulatory requirement is to endure 50 continuous hours of uncommanded fault injection. The engineers spend 50 hours actively trying to assassinate the virtual drone.
They inject pure chaos. They simulate a battery cell entering thermal runaway. They simulate a bird striking and destroying the pitot tube airspeed sensor. They simulate a massive spike of electromagnetic interference corrupting the CAN bus.
And every single time, the flight controller must perfectly identify the fault, mathematically isolate it using its RTOS partitioning, adapt its fuzzy logic boundaries to handle the degraded hardware, and autonomously execute a safe landing of the virtual drone. It has to do this perfectly, repeatedly for 50 hours.
If it fails a single time, if it crashes the virtual drone once in 50 hours,
You lose your certification path. You go back to the drawing board, you review the code, you tweak the MDO framework, and you start the 50 hours over from zero.
wow. Let's just take a collective breath and synthesize everything we've just unpacked. We started with a legal framework, the SORA and SAIL classifications, that are so draconian they demand 150 hours of mathematically proven perfection just to earn legal right to prototype.
We explored how engineers were forced to abandon linear design because of SWaP-C. They use AI neural networks and multidisciplinary design optimization to negotiate an impossible peace treaty between aerodynamics and structural integrity, resulting in carbon fiber shapes that save massive amounts of energy.
We looked at the combustion heart of the machine, realizing that gasoline still reigns supreme for energy density. But it's controlled by a FAEC system, a digital DJ balancing atmospheric pressure and fuel injection to prevent stalls, while mechanics monitor coolant pH to stop galvanic corrosion from quietly eating the engine alive.
We moved through the electrical nervous system, discovering that electric motors require real-time trigonometric illusions. The Clark and Park transforms to operate silently and efficiently, communicating over a CAN bus that enforces a ruthless 2-millisecond speed limit.
We dissected the multi-layered brain, a BMS that survives concrete drop tests, feeding into an EMS that utilizes model predictive control. That stunning J of X U equation that constantly gazes into the future, simulating realities to find the absolute most efficient way to fly without draining the emergency battery.
And we wrapped it all in the unbreakable armor of DO-178C software standards, eradicating dead code, partitioning memory like a digital fortress, and subjecting the silicon to 50 hours of virtual torture.
It is genuinely mind-blowing. The next time you see a commercial drone surveying a power line or delivering supplies, I hope you don't just see a large toy.
Right.
Inside that carbon fiber shell is a dizzying, invisible symphony of thermodynamics, fluid dynamics, advanced calculus, and artificial intelligence, all working flawlessly together thousands of times a second just to cheat gravity.
And I want to leave you with a final thought to ponder. Based on the trajectory of everything we've discussed today, we highlighted how AI proxy models are now autonomously determining the optimal physical shape of the wings. We explored how the MPC algorithms are continuously looking into the future, deciding how to expend energy, dynamically adapting their own fuzzy logic boundaries, and rewriting their own control gains as the hardware ages, all entirely without human intervention.
They are designing themselves, and they are teaching themselves how to fly their aging bodies.
Exactly. So the provocative question is this. At what point does a complex UAV stop being a mere program tool, executing a rigid set of human instructions, and start possessing an artificial engineering instinct that actually surpasses human intuition?
That is a staggering thought. We started this deep dive talking about the comfort of an X-ray, our deep human desire for a clean, binary, easily understandable diagnosis, broken or not broken.
But as these systems of systems become infinitely more intertwined, driven by predictive AI and constantly mutating multidisciplinary algorithms, the X-ray of how they actually make decisions is becoming murky again. We are building machines so mathematically perfect and so complex that very soon human engineers might not fully comprehend how they are staying in the sky. We will just have to trust the math that they do.
And on that slightly terrifying but utterly fascinating note, we are going to wrap up this deep dive. Thank you so much for joining us on this exhausting, exhilarating journey through the absolute cutting edge of UAV engineering. Keep questioning the world around you, keep looking up, and keep diving deep.